Hey everyone, and welcome to This Explainer. I am so thrilled you're here with us today. When we look at the physical world, it always seems so perfectly ordered in textbooks. But out there in reality, it is inherently chaotic. Honestly, it's messy. So today we're taking a really fascinating journey into the rigorous tools and techniques that physicists use to extract pure, undeniable order from all that chaos. We're going to look closely at the real-world practical skills of experimental physics. But right off the bat, I want to throw a question out to you. Is a perfect measurement actually possible? Well, the short answer is no, absolutely not. Every single measurement we make, no matter how incredibly advanced our equipment is, has limits. There's always this constant battle between the true signal we want to find and the noise of reality getting in the way. And that is exactly why practical experimental skills matter so much. We literally have to learn how to manage that noise. Okay, let's dive into this. Here's our chronological roadmap. 1. The scientific method. 2. Planning your experiment. 3. Mastering uncertainties. 4. The power of graphs. And 5. Evaluating and improving. Phase 1. The scientific method. This method is basically the historical and philosophical foundation of everything we do in physics. See, physicists have been obsessed with precise measurement for centuries. Long before we had fancy digital sensors, scientists started by just observing, measuring, and collecting data to find patterns. A really classic example is the 16th century astronomer Tycho Brahe. This guy spent years meticulously measuring the angular elevations of stars. Why? Because you can't just invent a theory out of thin air. You need to gather rigorous evidence first, see if it fits a pattern, and only then do you develop and test a theory. The scientific method completely demands that observation comes first. Moving on to Phase 2, planning your experiment. We're moving to the modern drawing board now. Because before you touch a single piece of equipment, you need a rigorous plan to handle that inevitable messiness of reality. Effectively planning an experiment breaks down into 4 critical stages. First up, you define the problem and identify your variables. Second, you outline your method, like what instruments will you use and what's the sensible range of measurements. For example, if you're testing a spring up to 20 newtons, you can't just test 12 to 20 newtons. You need a nice equal spread from 0 to 20. Third, you plan exactly how you'll analyze that data later. And fourth, please never forget safety precautions. A rigorous plan includes identifying hazards early so you don't do something crazy like accidentally electrocute yourself with a high-voltage power supply. Now, a massive part of that planning stage is defining your variables crystal clearly. You really must know your independent variable. This is the dial you are turning, the one the experimenter intentionally alters. On the flip side is your dependent variable. This is the quantity that changes as a direct result of what you altered. By firmly establishing these limits, you shut out the environmental noise and set up a fair test where you're only looking at the relationship between these specific things. All right, part 3, mastering uncertainties. So now we step from the drawing board to the actual lab floor. And listen, uncertainty is not a failure. It's just an unavoidable physical reality that we have to mathematically master. So the crucial point here is untangling 2 words that people constantly use interchangeably: accuracy and precision. Accuracy refers to how close your measured value is to the true or known value. Think of it like hitting the exact center of a bullseye. Precision, on the other hand, is about how close a set of measured values are to each other. It's all about repeatability. You can actually have incredibly precise measurements that are tightly grouped together, but if they are far from the true value, well, they aren't accurate. And this lack of perfection comes from experimental noise, which we categorize into distinct errors. Systematic errors are consistent shifts from the true value, always in the same direction, like if you're using a weakened spring in a force meter. Random errors are unpredictable variations around a mean, often just caused by human judgment. And then there's a zero error, which is a specific type of systematic error where your instrument reads a value when it should really read 0. Now here's a cool trick. Random errors can actually be reduced simply by taking multiple readings and averaging them out. But systematic errors? Averaging won't save you there. You have to physically fix your technique or completely recalibrate your tools. Let's try to anchor these abstract errors to a concrete example, just to make it real. Imagine measuring the maximum displacement of a swinging pendulum bob. Even if your ruler is absolutely perfect, human observation adds a massive layer of random error. I mean, you have to visually judge the exact fraction of a second the bob stops and turns around, and simultaneously read the millimeter mark. Sometimes you'll read it a bit early, sometimes a bit late. That is unavoidable uncertainty in action. So because we have these uncertainties, what actually happens when we use our messy measurements to calculate something else? Well, We have to use strict mathematical rules for combining uncertainties. Here's how it works. If you're adding or subtracting quantities, you add their absolute uncertainties. If you are multiplying or dividing, you add their percentage uncertainties. And if you raise a quantity to a power, you multiply its percentage uncertainty by that power. The huge takeaway here is that uncertainties always compound. They snowball. They never just magically cancel each other out. Okay, phase 4, the power of graphs. Let's step out of the lab for a second and head into the analysis phase. This is where we use visual tools to filter out all that noise we just mathematically calculated and reveal the underlying mathematical signal. But before we plot anything, we have to label our tables and axes correctly. The strict convention in physics is to separate the physical quantity and its unit with a slash, so time/seconds or diameter/millimeters. Why do we do this? Because a physical quantity contains a pure number and a unit. By dividing the quantity by its unit, you are mathematically left with a pure unitless number. It basically makes it algebraically correct to plot those pure numbers along your graph axes. And this brilliantly illustrates what we actually do with those plotted points. On the left, we see a line that's just simply connecting the lowest point to the highest point. And yeah, this is wrong. On the right is a proper line of best fit. It acts as a visual average. What you want is an even distribution of points above and below the line along its entire length. This is exactly how we visually smooth out all those random errors we discussed earlier to find the true underlying trend. But of course, reality isn't always a straight line. When your data follows a curved trend, you must draw a single smooth curve. You should never just play connect the dots with straight, jerky lines between data points. The physical world moves smoothly, and your curve should definitely reflect that natural arc. Now let's look at some slightly more advanced graphing techniques. In highly detailed graphs, we draw these things called error bars on our data points to visually represent our calculated uncertainties. This allows us to draw what's known as the worst acceptable line. This is the steepest, or the shallowest, straight line you can possibly draw that still manages to pass through every single error bar on your graph. Finding this worst acceptable line allows you to calculate the maximum and minimum possible gradients, which gives you a definitive, mathematically proven range of uncertainty for your final result. So let's see how this builds into an amazing mathematical hack that physicists use. What if your relationship isn't a straight line, but an exponential or power relationship, like y equals a times q to the power of n? We use logarithms. By taking the log of both sides, we actually transform that curved equation into the standard equation of a straight line, y equals mx plus c. If you plot log y against log q, boom, you get a straight line. The gradient reveals the power n, and the y-intercept unlocks the hidden constant a. It is a remarkably elegant way to analyze some pretty messy curves. And finally, Section 5, Evaluating and Improving. This brings us to the final step of our scientific journey. Look, no experiment is perfect, and acknowledging that is a core physics skill in itself. We have to constantly look at the limitations of our procedures and ask, how can we do this better next time? The most direct way to shrink our uncertainty is to simply upgrade our tools and techniques. If you're measuring the diameter of a thin wire with a standard millimeter ruler, your percentage uncertainty is going to be massive because the tool is just too blunt. But if you swap that out for a micrometer screw gauge that measures to the nearest 1/100th of a millimeter, you instantly and drastically reduce your uncertainty. Upgrading your tools pushes you that much closer to the absolute truth. Which leaves us with this final thought. We started out today by agreeing that a perfect measurement isn't actually possible, but by methodically planning, tracking our errors, mathematically combining our uncertainties, and visually graphing our noise, we find the truth anyway. The true genius of physics isn't in making perfect measurements. It's in perfectly understanding our limitations, because acknowledging exactly how wrong we might be is exactly what gives science its ultimate power. Thanks so much for joining me on this explainer. I really hope it completely changed how you look at the messy, beautiful world of experimental physics.